This is AP Calculus Lesson 10-1. We're talking about the general fundamental theorem of calculus applications. All right, so first of all, you know FTC, that does stand for the fundamental theorem of calculus. And in our words, that's basically saying that start plus change equals the end. So I want to talk about specific functions first of all. So a specific function is something where I have it equal to a bunch of numbers. So, whoa, what's going on? For an example, on the side over here, we can say, like, if you wanted, you could say Wt is equal to, I don't know, 3 cosine of t. It is a function that has something on the right-hand side. We know exactly what that specific function is, either by the graph, by an equation, maybe by a table, kind of, but it is equal to something. So if I give you a value of w, what's the derivative of w? How do I write that? Yeah, w prime. And another way of writing that we should get used to as well is dw with respect to whatever I'm giving you. It can be with respect to x. Usually on these it's going to be with respect to time, so I'm going to write dt. So using the same form, by the way, if you want to know who popularized this form, it was Leibniz. Kind of a fun fact. Anyway, have you guys ever heard of the fight between the two calculus lords, Leibniz and Newton?
No.
I think I'm pronouncing Leibniz correct, but it was over who invented calculus. And
Who did? Who do you think actually?
Well, I know what happened. Newton invented it, and then he didn't tell anyone about it. So then when Leibniz came along, he's like, "Here, I found it," and then Newton said no, and they got into a huge fight. And then Newton destroyed Leibniz with all of his influential power and made Leibniz die alone with no friends.
Oh my God.
Okay.
I feel like Newton was like a terrible person.
He kind of was. So, okay. So if I use the same form, Leibniz form, and I write the second derivative, what is that going to look like? Do we remember what second derivative looks like?
Oh, like dw squared or d squared w
D
over d. Just like
dt
there's a
squared.
form.
Yep. Squared goes in between and then off to the right. Exactly. All right. So that is the actual function. So if I come over here and I talk about the general function, that's going to be what? And we can use primes over here. I'm going to start being lazy after we know this form. The first derivative is going to be
F prime of x.
f prime of x. Second derivative is
F double.
exactly f double prime of x. And that happens all the way down. So if I gave you a position, so I'm talking about a particle now, usually you'll have these three vectors. So position vector. Do you remember what letter we say for position? Position. Usually we say that's x or y of t. That would be your position. We can write position under there. And almost always when you're talking about a particle, all of these are dealing with particles for this line. You're almost always going to have a specific function. They're not going to say, in general, a particle does this. So that's why I'm putting it in the specific function category. So position, and when I take the derivative of position, I get what function and what does that function represent. So what's the letter first? I take the derivative of x
So you
of
get
t.
v of t.
V of t, exactly. And what does vt represent? You said it already. Say it again.
Velocity.
Velocity.
Wait, what does that say?
Position.
No.
Oh, particle. I spelled it.
Particle-y?
Particle, yeah. And not Kaylin, someone new. When I take the derivative of velocity, I get, use your physics knowledge, a of t. And what does a of t represent? Acceleration, there it is. And then I guess if you want to use Leibniz form, again, let's just do one more for the general. If I just gave you y, instead of saying f of x, I'm just going to say y. Use Leibniz form, what's that going to be? Fractional form for this general function. It's very similar to this line right here.
dy over
dy with whatever you're taking the derivative with respect to. Let's say we're taking it with respect to x in this case, dx. Okay, and then second derivative is going to be what? Try not to look at your notes. Second derivative is going to be what?
D squared y over dx squared.
Perfect, yep. All right, so what do each of these columns represent? They all represent the same thing in terms of the specific versus the general. So in the specific, this is going to be some value. Same thing for the general function. If I just gave you a function, that's going to be a value. If I take the derivative of the value, what is that going to be? It starts with an r.
RT.
No, not quite.
RT.
It's a 4-letter word.
Rate.
There it is.
Oh.
Rate of the value. How fast is the value changing?
Oh.
So we'll say this is the rate of the value. Okay, and then using similar terminology, what is the second derivative? How can we think about the second derivative in terms of value and the rate of the value? Second derivative is what?
Rate of rate.
Yeah, exactly. It's the rate of the value. So rate of rate.
Oh, that's hard. Rate of the rate of that.
And another way of saying that is it's how fast the rate is changing. So this is how fast the value is changing for the rate. And now the second derivative is how fast is the fastest changing. How fast is the rate changing? So rate of rate again over here. How fast am I changing? So this is kind of all review up to this point, and I'm basically going to do another piece of review for the second slide. I'm going to wait until we finish writing though. I want to talk about the difference between specific versus general.
I feel like I don't like it.
Okay, so FTC, what does FTC stand for again? I already told us at the beginning of the lesson. FTC?
Function theorem.
Fundamental theorem
Oh,
of
yeah.
calculus.
There it is. Thank you, Isabel.
Close kill.
Of calculus. And this FTC, fundamental theorem of calculus, to us, it basically just means this. It basically means that the start plus change is equal to the end. So whenever you see FTC or fundamental theorem of calculus, be thinking of our generalized formula, start plus change equals end. Or alternatively, end is equal to start plus change. So I'm going to kind of flip this around. I'm going to say end equals start plus change for the notes over here. So I'm going to say end, and I'm going to be making kind of a table over here. End is going to be equal to start plus change.
How much room should we like leave in between them?
In between, so the change is going to be the biggest category. All of these are going to be basically like 2 or 3 symbols. So I'm going to do kind of a dashed line here.
I totally forgot that they still had to do
Me too. Like I was like ready to like.
All right, so let's start by finding, I want to find the position of W of 20. Yes.
Borrow one of your metric rulers.
I don't have, oh, I do have a metric ruler. I need it back though, thanks.
You're so sassy, Mr. Smith.
Well, I've had so many rulers been stolen, so I'm starting to number them now.
Oh god.
All right, so how do we abbreviate the start using this type of notation? So W of something. W of 0. Why W of 0?
Just because like that's 0 is like your starting place.
Yeah, so assuming that we're starting at time equals 0 or position 0, we're plugging in that, and that is going to give us, I guess it would be a time equals 0, and that will give us our starting point. All right, and then how are we going to find change of our function w? So this is relying on our last unit. Our last unit said we can take the rate, and then we take the integral of the rate to find the total change. So I basically just told you the answer. If you can kind of regurgitate that in a different way.
So you take the derivative and then take the antiderivative?
Yeah, exactly, yeah. So what am I going to write here then?
W prime.
So yeah, so you can say dw with respect to t, we're going to make t the variable. So we're going to take the derivative, and then what are we going to do with the derivative?
Take the antiderivative. Oh, so do like the integral of d.
Antiderivative, and then this is going to be dt. And now what am I going to have for my bounds?
0 to 20.
0 to 20, exactly. So we're basically reverse engineering what do we need to find in order to calculate the end value. All right, so let's try another one, just to make sure we know what we're doing. X of 5, and x is just a normal function. It doesn't actually mean position or anything, it's just a letter that I chose. I guess I should change that, but whatever. X of 5, what am I going to plug in for the next two slots?
X of 0.
X of 0, perfect.
And then you do your integral.
From,
0 to 5.
perfect.
And then d of x over.
Yeah, let's just make it t again. dt, dt. Yeah, perfect. Let's talk about the difference between velocity, acceleration, and position now. So let's say I gave, I'm looking for velocity essentially. So I want to find the velocity at time equals 3. Time equals 3. So this is t equals 3. How do I find the velocity here?
Just take the derivative.
Take the derivative again. So again, you're going to start at the velocity, your initial velocity, right? So what am I going to write here for initial velocity? V of 0. And instead of writing a derivative over here, we know the derivative of velocity. So this is going to be what over here?
Just vt dt.
So yeah, so you would be saying the derivative of velocity, which is what you're saying, Kaylin, but we know what the derivative of velocity is equal to based on our last slide, right?
Oh, so just a of 3.
Careful here. It's still going to be an integral because a of 3 is just going to be the acceleration at time 3. You can't add acceleration and velocity.
Oh, so then the integral of at dt.
At dt from?
From 0 to 3.
Perfect. Yeah, exactly. Okay, and then let's try so all of these so far have been specific because just by how I'm lettering them. So let's say that all three of these, bless you, all three of these are specific. When I give you a W, an X, or a V, you know I'm talking about something very specific. But if I gave you a general formula like a function f of b or g of b, then I'm talking about something general. So let's do a general one, just kind of an f of b. I don't know what number I'm looking for, so this is general. In general, how can I find any b? And we've seen these on tests before, so we kind of know what to put over here. What is my start going to be for my general function of b?
F of 0.
F of 0, yeah. It's still f of 0.
I thought you were going to say it, so I was like,
Yeah, I thought you were going to say.
And what am I going to have on the right-hand side?
Oh, then 0 to b.
Exactly. Yeah, that's the key. So from 0 to b.
Wait. I was like, isn't he right?
And then f of b.
Be careful here.
F prime of b.
F
Or
prime,
f b dt.
f prime of the variable. So whatever variable, it could be t or x. I guess we can just change it to x. F prime of x dx. What if we wanted to make this even more general? What if we didn't start at 0? What if we instead started at a general point a? Let's change that to an a. What would happen then?
We just changed the b. I mean, the 0 to 10.
Exactly. So you could make it even more general if you wanted. And the last one, I'm going to say, I want to find the general function g of b, and I'm going to start at a again, so find the formula. Try to do this without looking at your notes. Brand new, fresh, clean slate. I want to find the position at b on this general formula if I start at a. What is the formula that you need to write out? The n is going to be equal to, all these should be equal to's by the way. And I'm going to write it up on the board for you to check your work, but it's going to be very similar to your last line. I don't want you to look at your last line though. All right, check your work once you have your line written down. You can check it against the line above you. It's basically just changing out an F for a G. That's the trouble with specific. There's only so many ways I can write this. All I can do is really change the letter. It's pretty easy over and over again. All right, that's all I need to go over. It's pretty straightforward, but the homework is the hard part. All right, go ahead and write your summaries. What's the difference between specific and general in your own words? All right, so I'd like to go over the homework, at least the first problem on the homework. All right, so
You think it's gonna take that long? Oh wait, just for the video.
Just for the video, yeah.
Oh my gosh.
I was like, oh god.
So we're trying to find f of -3, but it gave us a graph of f prime. So you're just using your general idea from the notes. F of -3, what should that be equal to? So this is giving us an end. F of -3 is our end. We need to make that equal to our start plus change. So what is the start going to be? In general notation, you don't need to actually find it on the graph.
F of 0.
F of 0, exactly from the notes, plus
Integral 0 to -3.
Be careful here.
Negative
-3
to 0.
So -3 to, so you're actually right. So let me go through this. This is a little bit tricky. You're right in thinking it's from 0 to -3, but in order to get this correct, you need to flip them. Whenever you flip these two, and this is a rule in all of calculus, the integral now becomes negative. So what I'm going to do here is I'm going to flip these from -3 to 0 so that we can still think about it in the same way, but now I'm going to make it a negative. So it's going to be f of 0 minus -3 to 0. And this is going to be what on the inside here? Let's just do simple notation, no Leibniz notation. F prime of x dx, there it is. Okay, now we need to actually find those things. All right, so we need to find the integral between -3 and 0. So we need to find, if we made this into all these shapes, from -3 to 0, we're just looking at these triangles here. So this triangle has an area of what? It's 1 by 1, and then half of that. So 1 times 1 is 1, divided by 2 is 0.5. Perfect. And what about this triangle here? 2 by 2 divided by 2?
2.
2. And be careful here, it has a negative area. -2. All right. So what is our start though? Is there somewhere in this problem that tells us what our start is? What is f of 0?
3.
3. Okay, so it's going to be 3, and I'm going to subtract, and then what is this going to be? 1/2 minus 2, that's going to become
Negative.
-1.5. So that's going to be equal to, negatives kiss, become positive
4.5.
4.5. There it is.
Ew. That wasn't too bad.
All right, so that was just doing the first one.
Not too shabby.
Now we're going to do the second one. F of 4.
Are you?
F of 4 is going to be a little bit more difficult because we're dealing with circles. All right, formula for F of 4.
Oh.
Equals f of 0
F of 0,
plus integral 0 to 4
0 to 4,
f prime of x.
F prime of x dx. Perfect. Now we just need to find all these things. All right, so we know our start from our previous problem. Start is always 3. And then the integral between 0 and 4. So now we need to find all of that area here. So this shaded area right here, this shaded area right here. Anyone have an idea for how to find that?
Oh god. Maybe like.
So this is a semicircle right here, which means it's exactly half of a circle.
I was like thinking that, but then I was like, how would it work? Because it's like. So then we could find the area of the rectangle and then the circle and then just subtract it.
Yeah, so Kaylin is saying find the area of the rectangle, subtract the area of the semicircle, and then you'll get what we're looking for, which is this part right here and this part right there. Okay, so find the area of the rectangle. Area of the rectangle is, it goes out 4, down 2,
-8.
-8. I like how you had the negative in there. And then we're going to subtract the area of the circle. So the circle has a radius from here to here, so that radius is 2. And what is the formula for a circle as well? The area for a circle is equal to
Pi r squared.
pi r squared. Perfect. And we know our radius, which is 2. So this semicircle therefore has an area of,
4 pi.
careful, it's a semicircle, not a full circle,
Oh, just 2.
2 pi. Yeah, so you did 2 squared, so 4 pi, and then half of that is 2 pi. And that's going to be a negative area also. It's below the curve, right?
Yeah.
All right, so therefore our final area is
8 plus 2. 10 pi?
Negative. Oh,
No.
So it's going to be -8 plus 2 pi. All right, so we just need to add that area. So this is going to be plus our -8 plus 2 pi. That was the area that we found up here. And simplify that a little bit to get -5 plus 2 pi. All right, easy peasy lemon squeezy.
meh.
Meh. All right, all the problems are going to be roughly like this. Let me see if there's anything a little bit hard. Ooh, that problem at the very bottom is going to be hard.
Can we do it?
Let's see if we have, what time is it right now?
10:41.
Yeah, we can do it, okay. So let me make this a little bit smaller. Grab this, paste this, grab all the things in here, except those, delete, and let's grab this problem down here. Ooh, yeah, so that's going to be a little bit difficult. Let's see how to do this. So this would be problem 3, I believe, if we're labeling these. All right, so we have all of this information, and we need to write the equation for the line tangent. So line tangent, what is our general equation?
Y
Yep,
minus box equals slope
yeah, that's going to be the slope here,
parentheses
parentheses,
x minus blank.
x minus blank. I gave big boxes here because these are going to be long decimals that I'm going to have to put in here. I can already tell just by looking at this garbage equation. It's kind of complicated.
Garbage.
All right.
Are we not allowed to use calculators?
We are going to have to use calculators here. So let me pull that up also.
Can I borrow a calculator?
Yeah.
There you go.
So what am I going to do for this one? So we need to have all three of these points. Do we have any of them already?
Yeah.
Which one?
X.
What is x going to be? What should you're saying this box right here?
I think
Yeah, what should it go in there?
2.
Yeah, exactly, because it told us we need to put in 2 for x. Okay, now we need the slope and we need this point right here. So this is going to be what? What goes in here? What do we need to evaluate?
When x equals 0, we can solve.
Not exactly. So this needs to be the y-coordinate, right? This is the x-coordinate. This is going to be the y-coordinate. So we need to go and find
Oh, when x equals 2.
when x equals 2. So this is going to be f of 2 that goes in there. And what goes in the slope?
F prime.
F prime of 2. Perfect. Yeah, okay. So which one do we want to find first?
Maybe y.
Just the f of 2 right here? Okay, so f of 2, how are we going to find this? And how does it relate to the unit? We're on Unit 10, Fundamental Theorem of Calculus. One of these 3 boxes is going to be the Fundamental Theorem of Calculus. It's not that one because that's 2.
I think it's going to be the f of 2, right? Because they give you f prime of x.
You are correct. So f of 2, write out our formula. F of 2 is equal to.
They don't give us enough space here.
I know. I didn't give you enough space. That's my fault.
You did not give us enough space.
F of 2 is equal to
5 plus. And then the integral from 2 to 5?
the integral from.
Or 0 to 5?
Go back to your notes. So in the notes, it was always from. That's not far enough. Did I get rid of a slide? Oh yeah, so here it is. It's always from this point to this point.
So 5 to 2?
No,
No,
Just 0.
0 to 2.
0 to 2, there it is. From 0 to 2 of our f prime, right?
Yeah.
Prime of x dx. All right, and we can do that on our calculator. So let's plug in our 5. Oh, maybe we should do our equation first. So our y equals, this is going to be second, where's e? Second natural log, so this is going to be e to the power of negative x divided by 4. And that's going to be multiplied times sine of, there's already an of x squared. Perfect. So we have our y1. Let's get out of that. And now we're going to enter this equation. So 5 plus, and then the integral is going to be, how do we calculate integral? What
Math
operation?
9,
Yep, math 9.
Vars, enter,
Vars right, enter, enter. Yep.
enter. Oh,
With respect to x from 0 to 2. There it is. And we get, yep, 5.623. So that's the number that goes in here. So this is going to be 5.623. And now we need to find f prime of 2. So how are we going to do that with our calculator?
Just do y1 of 2.
Exactly, yeah. So vars right, enter, enter, y1 of 2. Plugged in 2. And that's going to be negative 0.459. And we're done. That's our equation. We don't need to do anything else to this equation. Is there any other hard problem on here? Nope, all of the other ones are pretty simple. So the next problem, number 4, is very similar to this problem, and 5 and 6 are similar to number 1. So good luck on the homework. You want to say goodbye to all the people watching the video?
Bye.